So no visit to IBM research would be complete without an exploration of the future of computing. So IBM obviously has a long history of inventing computing technologies that change the art of the possible for business, government, and society. So I'd like to invite Darío back on stage to share his vision of where computing is going. Darío.
Thank you. Thank you. And I'm going to start with an observation, actually, from Ingrid this morning, where she spoke about an intellectual feast. And in the process of engaging with her PhD students about building an intellectual landscape that allows you to traverse. And I want to offer just a few sketches on that journey in the world of computing in a way that hopefully illuminates some of the more fundamental technologies that we're going to see unfold in the next 5 to 10 years in this field. And for that, I want to establish another connecting issue to a thread that has been present throughout the day. And that is the power of information representation, and how when we change the lens with which we represent information, it opens all sorts of new scientific and business opportunities. And that is, of course, the case also in how we will drive science forward. And I'll offer that in the world of computing, one of the scientific leaders that have helped us even to this date date back to an idea that over 300 years ago from Leibniz. And Leibniz already had this insight, and this is this great quote: "To create everything out of nothing, one is sufficient." And he had this insight that we could take the knowledge of the world and represent it in binary format. And that once we could represent it in binary format, we had the potential to use, as Ingrid said, all the tools of mathematics to make our way forward to a more perfect understanding of the world around us. Now, famously, in our world of computing and information science, that original insight was codified mathematically by Claude Shannon. And Shannon described information as the resolution of uncertainty. And after that core idea and the core mathematical principles of what is now known as information theory or classical information theory, really we could not see the world the same again. All of a sudden, this information lens was present in the minds of scientists and engineers, and over time, business leaders, and that objects as different as an old punch card or DNA that prior to those insights would have been seen and tried or attempted to be understood through different tools and mechanisms, all of a sudden we could see them as information processing systems, as actually a way to understand very disparate physical manifestations of how to encode information and how to read information and how to process information. In fact, we've also seen that as a consequence of that, a wide variety of information representations have been created, of which this is just a tiny sketch. There have been ways to represent information relationally. We have seen spectral representations of information. We've seen graph representations, you name it. I'm sure many of the people in the audience could name many more. And it's been interesting that once information representations have been created, there's also been extraordinary opportunities in the context of business for value creation. Now, let me touch on 3 elements of these sketches, just the pure power of the binary representation and how its relationship to technology and what is known as Moore's Law has had such a profound transformation, and I'm going to give you a number, a data number to look for of what is going to be possible to integrate by the end of the decade. And here the relationship I want to connect is, of course, once we have this information representation of the binary, there's all sorts of complementary ideas that build on top of it. And one of the most fundamental was that you could encode information in physical objects, and namely with the invention of the transistor, that we could actually create a device, a switch that represents that 0 and a 1, but crucially and very importantly, that we could scale the number of switches that we could integrate per unit area exponentially. And this has been the collective effort, which is a second theme of my remarks, of a wide variety of institutions. And part of my remarks is a collective celebration of the institutions that carry out science and technology, and how we build very complex networks that build on each other, from national laboratories to universities to business, all working and building and moving a field forward. This simple little plot here that you see the number of transistors growing is literally the collective effort of hundreds of thousands, if not millions of people, of scientists and engineers, and a cumulative investment that adds in the trillions of dollars without a doubt, to be able to have that level of integration per unit area. It is the consequence of that that has allowed us to build every imaginable computing system. We had Travis before talking about in Oak Ridge, right, building the world's fastest supercomputers, or it allows us to create derivative versions of semiconductor technology to express even novel forms of computing, and you name it. But this aspect of the collaborative endeavor is also something that in my dreams have aspirations to do in gatherings such as this. It is each of you represent incredible institutions, and through these networks and through this curiosity of learning from each other, it allows us to work with one another to advance the fields. And this, I just give you an example of a public-private partnership here in New York that is the result of over $15 billion of investments over 20 years in the effort of pushing the limits of transistor technology. So through an effort like this, one of the things we're very proud that was created was the next generation of transistor. It's called the gate-all-around technology, that it is going to be the basis of all future semiconductor technology beyond the 2 nanometers. So in the future, quite literally every device that you will all use, phones, computers, and you name, will be the effort of a collaboration that has brought material scientists, semiconductor specialists, and of course, fabrication specialists to make something like that happen. And here's where I give you a number. By the end of the decade, we will be able to integrate, thanks to those advances, and advances are happening in packaging, in chiplets, 1 trillion transistors in a chip the size of a fingernail. It's one of those things, it's like hard to overestimate the implications, because when you're dealing with exponentials, for a long part of the exponential, to a lot of people, it feels like the doubling is in the flat side of the curve, right? But the last doubling, right, when you go from 100 to 100, it is one of those things that I think the world comes out and says, what happened? What occurred? And what occurred is this long story, right, manifesting itself. So that's one data point I'll give you of what is going to be possible with semiconductors. In fact, the semiconductor story now is intimately tied to the economic and national security of nations. And I want to give you just a little anecdote about the scale of efforts and investments going on. This is a picture that was taken on May 22, 2023, in the north of Japan, in Hokkaido. And it was a field like that. We went on there were Land Rovers and so on, totally empty, okay? So it's May of last year. This is a picture of what that is looking like 1 year later. These are like nation-scale efforts trying to revive advanced semiconductor manufacturing, for example, in Japan. Similar efforts are underway, by the way, in the United States, in different areas, because it is not a gross understatement that the ability for us to secure semiconductors and take all of that knowledge that we've been talking about and encode it in silicon to power all the imagination that has been put forth through today's dialogue is going to depend on our ability to source that, to have access to that technology. And those are nation-scale investments that require a massive collaboration. I want to now offer a second observation on AI and what is happening right now with the neural network representation of the world. And to that, I was just going to make a simple point. And it's an interesting contrast between let's call it the natural experiment that has been conducted in the industry of taking all the public data available on the internet and encoding that data inside a neural network representation. I mean, Jan talks about that these future AI systems are going to represent literally all the cultural knowledge of the world, right? It's all going to be present in there, and we're going to engage with that. But just to offer the contrast that that has occurred with all the public data, and particular modalities of it we know are heavily indexed towards that, of language and code and so on. But in general, as a little bit of a provocation, just to offer the observation that if we ask what percentage of the institutional data that is present in enterprises or in universities or in national laboratories has made its way into this new form of information representation, we would say very modest. We're just at the beginning of that journey. And that the task ahead is going to be to have the creativity to, in a well-engineered scientific manner, to have more and more of those modalities encoded in this representation to exploit its unique advantage in terms of multimodality, in terms of the scale of the connectivity and semantic connections that we can create, et cetera. But for that to happen, for that collective effort to happen, we are going to have certain principles with which to collaborate with one another and carry it out. And open innovation is going to be an indispensable element for that to occur. We're also going to have a vision where optimized models of a wide variety can be created and shared with one another. And we know that these environments are going to be hybrid in nature. Some of it will be entirely appropriate to do on the cloud. Some will have to be next to a scientific instrument or capability on premise. And there could be other security requirements that allows you to have, some will happen to have in the edge. So hybrid approaches for how AI will be run will be important. And we got to have sort of this systematic effort for how we actually encode and represent that data. On this open point, we are incredibly passionate as advocates of why the future of AI needs to be open. First, just pure also technologically, right? Just an observation that over the last year and a half, the story, if you plot it, is a story of convergence of what open can do versus closed. And you just have to look at the graph and just extrapolate a little bit and just to be absolutely confident that open innovation will outperform, right? Technically and in capability, what is going to be done with many of the proprietary models. Also, and just to say a word on the business dimension of this, an open innovation and an optimized model that you allow for fast customization of enterprise data can outperform the largest closed models in the world at a fraction of the cost. These are real data of examples that we've done of doing the most commonly used use case for AI in the enterprise world, which is the world of RAG, where you have documents and you have to summarize them, dialogue with them, do things of the sort. And here you're seeing that you can actually build a model with just a few billion parameters, surely, yeah, trained with a lot of data, right? Maybe 12, 14 trillion tokens. But nonetheless, a small model in comparison to, like, say, a trillion parameter model like GPT-4 Turbo. And for the use case that you care about, which is dialoguing and summarizing documents and doing this stuff, you can outperform the larger model at 95, 98% of the cost. So there's a lot of opportunity in allowing us, all of us in our institutions, to be more facile and more viable of this data representation with our own data. And lastly, this topic of energy, right? We are all witnessing, I think Paul Dabar is somewhere here and tells me about like the insane number of power plants, like I think like we gotta build, just in one county in the United States, a gigawatt, right? A year, just to power data centers, just to give you a sense of what is going on. In fact, if you just look at the training of compute in terms of flops as a question of time, right? We have an exponential going on in there. No matter how you slice it, even if you take it all the way to the Landauer limit, right? But if you keep going like this, we will, essentially, if you just naively extrapolate it, what is going on in AI and just say scale, scale, scale is everything, we will end up using more than this energy in the planet, right, to be able to do. So obviously we know that that is not going to be the answer, and that the answer to this story is not just brute force scaling. So radically rethinking architectures will be important. In terms of GPUs are not going to be the final destiny of AI. They just happen to be better than CPUs for doing matrix multiplication and some of these areas. But ASICs and specialized with reduced precision architectures, removing the von Neumann bottleneck and co-locating memory and compute together, and in the future even analog compute, will be important elements to tame the energy monster, right, that is happening around this. And then a last word on this topic of institution building in AI. This is a picture of the AI Alliance, and and I feel good that so many of you at the institutions here are members of this. The origin of this started also with an email I sent to Jan, right? It was like a year, I don't know, and a half or something like that, where there was all this sort of debate, an apocalyptic debate happening in AI. There was a lot of this open versus closed. And we decided actually to do something that we did not see ourselves reflected in what the future of AI should be, and that the story was being monopolized by just a few institutions. And we decided actually to engage with so many of you, with leading universities, with philanthropies like the Simons Foundation, with small companies, large companies, international, that wanted to use their R&D resources and their talent and their passion to build a future of AI that wasn't apocalyptic, a future of AI that was built on open science and open collaboration, because that was the best way to ensure that it would be the safest way and the most productive. And this is a picture that looks very different than if we show the future of AI and we show you 2 dots in the West Coast, right? It feels different, and it needs to be developed that way. So we talked on the last element that I wanted to talk in terms of information representation. You saw from Jerry and the wonderful panel that we have that there's just another example of information representation is what's going to be possible with quantum computing. And this quantum circuit representation is going to be important, and the biggest task that we have ahead, and the only things I wanted to touch on this technology, is the collaborative ecosystem to allow more and more scientists to imagine how to operate and work with this new representation. What you're seeing here is a plot of the number of scientific papers that have been generated by using IBM quantum systems that we've made available to the community. And the purpose is to go from industry leaders and research institutions getting access, like our friends at the Cleveland Clinic who are here, to startup and a broad user community that can access this in a fundamental way. And the challenge we've been giving the community is essentially to say, stop doing small qubit experiments. We're now moving forward such that we have systems with well over 100 qubits. And what you're seeing is that the community is reacting where basically this is a plot of all, using all available quantum processors, that basically the entire community was just writing papers doing few qubit experiments. But as a consequence of some of the key advances that have happened with error mitigation, now all of a sudden you can actually do experiments that are hard to simulate with classical systems. And there's been a discontinuity as a consequence of these advancements. And I think now we have formed working groups with many leading scientists around the world in the areas of optimization and materials and high energy physics and healthcare and life sciences on this quest of discovering, sometimes there was a lot of interesting discussion between theory improvement and theoreticians and empirical advances in the area. We like both. Both are definitely fantastic ways to do this, but it is an invitation, right, for many people to think differently as we unfold towards the end of this decade in the ability to actually now create very large-scale computational systems, quantum systems that will work in concert with classical systems. So this brings me full circle to what I wanted to give you a sketch on the future of computing. I like to summarize it as just a way to remember of bits plus neurons plus qubits, just as a way to remember that it is not the story of just one thing. Our vision for the future of computing is to take the advantage of the best that you can do with high-performance computing and high-precision computation, with the best that you can do with neural network-based architectures, and the best that you can do with quantum computers. And that all of that needs to be integrated to behave as if it was a single computer, that will undoubtedly be assisted by AI programming, and that the nature of the problems we will solve will be a function of the ratios of how much we use of each of those systems. But that task is a task that we, as computer makers and information technology providers, should take on behalf of the user and simplify it. They don't need to worry or think about whether they're using this type of computer or that type of computer, but actually to benefit from the power of information representation that can happen at that scale.